And off we go. Okay, so here's where we were last time. So we were talking about this idea of an accumulating quantity. Let me rewind just a bit here. So, I've spent time previously making kind of vague reference to this idea of an accumulating quantity. The whole is the sum of the parts, right? It's not a super deep idea. And keep in mind, some quantities have this property, mass. Yeah, the whole is the sum of the parts. Of course it is. What else would it be, right? Area. Yeah, of course. You chop something into two pieces. The total area is the sum of the individual areas. Yes, of course, right? But not every quantity that you can define on areas will necessarily communicate. And I think perimeter is a lovely counterexample. The perimeter of this whole region doesn't include this little dividing line in between, right? But if you cut it into two pieces and you look at the perimeter of the left and the perimeter of the right, both of those perimeters do include this sort of dividing line in between, right? So the whole is not the sum of the parts. So let's just keep in mind, this property of accumulation. When you see easy examples, they're so easy that it almost leads you to believe that it's always going to work, but it doesn't. Okay. So next observation. This one's going to seem a little silly and pointless, and I recognize that, right? But it's not. This is actually going to end up being really important to how we approach several big theorems that are going to come over the next few weeks here. And that is that accumulating quantities, basically, they behave like physical stuff. Just to jump to the punchline. And what do I mean by that, by behave like physical stuff? Well, let's talk about mass. Mass is literally physical stuff, right? And if I were to talk about the amount of mass that's in a given region of area, I could, of course, also talk about how much mass there is in any one of these little subregions. Well, yeah, of course. Right? The mass is literally distributed across the area. Right? So the claim I'm going to make here is whatever accumulating quantity you have, even if it isn't physical, you can pretend that it is. You can pretend that it's distributed across the interior, just like area is. Because if you did pretend that, for example, the amount of work that it would take to build that area, or the amount of time that would take you to weed your vegetable garden or whatever, right? If you were to pretend that even though it's obviously not actually distributed, if you were to pretend that it is distributed across the area, and if you were to talk about how much of that accumulating quantity is in each little piece, well, that would effectively force you to accept the idea that, well, the whole must be the sum of the parts, which it is. Right? So the fact that it's an accumulating quantity is what allows you to make this choice, even if it doesn't really make physical sense. It's going to end up being strategically very convenient. Right? So I will be talking about accumulating quantities as if they are physical stuff, even though they aren't. And no problem. That's going to be the punchline. All right, so what can we do with physical stuff? If I'm allowed to treat it like physical stuff, what do we do with physical stuff? We talk about densities. Right? So with mass, right, we have this idea of mass density. The density at a point basically just says mass per unit area. Right? You got to be a little careful. Mass doesn't actually exist at a single geometric point. Mass is distributed across areas, but you can talk about the amount of mass in a region and then divide by the area of the region, and then take a limit as that region gets smaller and smaller, and as it gets teeny tiny, it starts to approach some limiting value, and that's what we call the density. It's an old concept, right? You may or may not have actually thought about it carefully like that, but this is what you're basically doing when you talk about density at a point. And why are we interested in the idea of density? Well, because a density is something you can multiply by a size to get a quantity. All right, so mass density, well, yeah, of course. Now, population density. Well, yeah, Same basic idea. Again, you can think of whatever it is that you're looking at the population of, maybe people, maybe ants, whatever. You can think of it as a kind of a physical stuff, right? And it's not such a crazy idea there. Where it gets a little weird is that if I take one of these quantities like work that isn't concrete physical stuff and say, well, yeah, but I'm going to treat it like stuff. I'm going to pretend that it's actually distributed across the region, then I can make this same calculation. And I can talk about how much work or how much, time to weed my vegetable garden or whatever it is, how much of that is in a given little region, and thus I can talk about work per unit region or time per unit area of region, and that would be something that I can multiply by area to get stuff, in this case work. So if you can treat it like mass, well, this is one of the things that we do with mass. So we can do this with any accumulating quantity. Okay. Then what do we do with densities? Well, we can write down old results like this one. Mass is an accumulating quantity, so the whole is the sum of the parts. Y'all have seen me write this down a bazillion times and almost apologize for how unnecessary it is sort of even to write this down because, yeah, of course it is. And then, further, we've a million times talked about how on any given little region, mass relates to area by way of density. So I'm going to call this a little theorem. You might call it the mass density theorem. And all it is just an acknowledgement that, look, when you have an accumulating quantity, as we discussed above, you can treat that quantity like it's a stuff. In this case, it literally is a stuff. And you can talk about the associated density and therefore write the quantity in question as an integral. That's all it is. Again, we've done that a million times. Right? Where it starts to seem a little eyebrow raising is when I do that with work, right? And I do the same argument, whole is the sum of the parts, pieces are density times size, and then we have this associated, again, work density, which is not something that's intuitively relatable on first glance until you realize, again, we have an accumulating quantity. Accumulating quantities behave like stuff. Stuff has a corresponding density. So you could call this a work density theorem, totally analogous to the mass density theorem. It just kind of requires a little bit of willingness to be flexible with how you interpret, how you visualize some things. Yeah?
Just one question.
Yeah.
I thought work was describing a vector of motion.
Well, yeah, exactly. So that's why this seems a little bit strange, right? So let's go back up here and look at this picture right here. And yes, you're right. One way that work can get created or work can be required is if you have a heavy thing that you want to move a certain distance against a force, right? Yeah. So this is a different kind of work. This is, I like to think maybe this is the bottom of a swimming pool, and for whatever reason, I'm stuck with the dirty task of having to clean the bottom of the pool, and I'm going to have to scrub. And for whatever reason, maybe the deep end has more ugly stuff on it that has to be scrubbed off, and maybe the shallow end not so much, or something like that, right? And so here the work is in how much do I have to scrub. So it's a different kind of work, and it's not force times displacement. Is that cool? Yeah. So still though, the total is the sum of the parts, and so it is an accumulating quantity. All right. Okay. So we are actually going to do, over the next few weeks, several examples of things kind of like this. I'm going to find some accumulating quantity that is going to be weird. It's not going to be it's not going to be something you would have thought of as being an accumulating quantity, but it is an accumulating quantity. So I can treat it like stuff, so I can talk about its density, and so I can write down an integral theorem. And we're going to get several massive integral theorems out of this approach. So that's the big picture. One last observation I'll make. I wrote this down in terms of double integrals and, areas and two-dimensional regions. You can do the same thing for three-dimensional regions and talk about quantities that accumulate over volume instead of quantities that accumulate over areas. And likewise, you can do this in one dimension and talk about single variable accumulating quantities that accumulate over intervals. Same basic ideas, just different dimensions. Okay, all right, now we're going to work our way up on this page to a new example of an accumulating quantity, but I have to worry about a detail of a definition first. I'm going to define what I mean by boundary. It's not such a new idea in some sense. Y'all are probably aware of the idea of that if you have a curve, then if it's a closed curve, that is, then you can talk about the interior, this green interior. And if I ask you, what's the boundary of that green region? Well, it's the red curve. The boundary is the border between where the set is and where the set isn't, right? So that's one way to think of boundary. We are going to add now to this idea. The word boundary now means more than just the border. Now boundary is an oriented thing, right? Boundary is oriented. Henceforth, for the rest of chapter 6, for the rest of chapter 7, that word boundary means oriented according to very specific conventions. So starting with this two-dimensional region, here's the convention. The orientation says wherever I might happen to be on a piece of the boundary of some set. Now I just kind of zoomed in on what would appear to be kind of the bottom part of some region D here, and you can see part of the boundary, this curve right here. If you're at that point, the orientation says which direction do you need to go so that the region is on the left. And notice that's the case here, right? If you imagine yourself walking along this boundary curve, right? At this point, you have to go that way to have the region actually be on your left. Everybody see that? If I were going the other way, if I were walking this way, the region would be on my right. And that doesn't obey the convention. The convention is region on your left. Real quick, an acknowledgement, this is a completely arbitrary convention. Somebody made it up. Somebody pulled it out of a hat, pretty much. And the thing is, it has become a standard. And so it's not optional, right? This is the way planet Earth works, and so everybody's got to get on board and speak the same language. So always on the left, not for a mathematical reason, just because of, well, let's call it social convention, I guess. Okay. All right, so now another example. Same region D, but if I were to look kind of at the top part of this region, D is down below here now, and if I look at this part of the boundary curve, right here, well, I would need to go that way in order to, again, satisfying the rule, I need the region to be on my left. And that's the way I go to have the region be on my left. Everybody on board? Yeah.
If it's at right, then the arrow would point the other way.
Yeah, that's right. But very importantly, left. Yeah.
Yeah.
Yes, exactly. Okay, now one thing you're going to notice pretty quickly is that if you have what I'm going to call a really simple region like this that loosely speaking doesn't have any holes in it, we'll deal with stuff like that in a second. There is a nice simple version of this when you have this is technically called a simply connected region. Details you don't need to know. The direction you go to have the region on your left also has the feature that it's always counterclockwise, and that's lovely. Nice and convenient, counterclockwise. Here's the problem. It is often, because of how convenient this little shortcut is, it is often overstated that this is the rule. It is not. This is not the rule. This is a convenient coincidence that is true most of the time. But let's notice it's absolutely not true all the time, because if you were to look at a region like this one, now at that point you go that way. Yes, that's counterclockwise. If you're at this point, you go that way, and yes, counterclockwise. But if you're at a point like this, on part of the boundary that's, what you might call the interior part of the boundary, because it's got this cookie cutter hole cut out of the middle of it, the direction you would go to have the region on your left is like that. And that's not counterclockwise. Everybody see that? Yeah, question?
Is that why we usually talk about curves in R2, like when we're doing line integrals, as oriented counterclockwise too?
Let me think about that. The convention, the counterclockwise thing, is due to it being part of the. That's the convention for boundaries. And like if you look at the unit circle, it is true that the unit circle is more often oriented counterclockwise, right? But it only has to be oriented counterclockwise if you're thinking of it as being the boundary of the unit disk. So it's the word boundary specifically that requires this convention. If somebody just says, hey, unit circle, which direction is that oriented? The answer is it's not oriented because you haven't told me an orientation yet. Does that make sense? Yeah. Okay. So there is, in other words, there's no standard orientation on on any curve that is just defined on the basis of just being a curve. Yeah.
I'm a bit confused. Like, what told us that we would have to draw it? Why is it inside? Why is it not the other way?
Well, because again, the region's got to be on your left, right? That's the rule here. Whichever way puts the region on your left, and if you look at this point right here, going the way that I've got marked there. Notice, get this thing to settle down, the region's on my left, so that's the correct answer. And this counterclockwise rule is a red herring. That's not the rule. It's a coincidence most of the time. It's not the correct rule.
Thank you.
Yeah. Okay, so here's the big reveal. Our new accumulating quantity, weird accumulating quantity that's going to end up giving us an unbelievably cool theorem. Accumulating quantity in question is boundary circulation. Now, you will have noticed the word boundary, right? By the way, you need to promote in yourself a knee-jerk reaction when you see that word boundary. He said boundary. That means orientation. We've got to worry about the which way is this oriented? Start thinking about orientation, because that's what that word means henceforth. And I'm now realizing, by the way, I forgot to mention something, a notational point. Coming back for just a real quick second. This notation, that symbol right there that we usually use for partial derivatives, is also a fairly standard notation to represent the word boundary. So I'm going to be using that a lot. It's very convenient. Why do we use a partial derivative? Well, there's kind of a vague sort of a reason that I could give you, but it's not worth our time to discuss. So anyway, heads up, that means boundary. And so I claim that boundary circulation is an accumulating quantity. All right, let me try to persuade you of this. We will start with what I'm calling D1 here, this region on the left. You'll see, of course, there's a larger region, and I've kind of split it down the middle to create D1 and D2. You can see the accumulation scenario coming up. So there's my D1, and let's talk about the boundary circulation on D1. It means exactly what you would think it means. It means I'm going to go around the boundary following the rules of orientation, and I'm going to compute that circulation, namely vector line integral defined on that oriented curve. That's what we mean by boundary circulation. Is that cool? So this here is the boundary circulation for D1. Let's see, now let's talk about D2. D2 being the other side, if you will. And let me just color that in. So D2, if I wanted to draw a picture of the boundary circulation for D2, well, again, go around the boundary, follow the rules for orientation, and line integral on that curve. Okay, well, region on my left has me going about like that. All right, that's the boundary circulation for D2. And now let's ask, what do I get when I add those up? If I take the boundary circulation for D1 and add the boundary circulation for D2, adding those together, well, let's see here. Let me get rid of the colors there. What do I get when I add those up? I'm not happy at first glance, because I look at all this stuff in the middle and I think, well, you know, that stuff in the middle, that's not part of the boundary of the union, right? If I look at the whole lump there, that's not part of the boundary. How could this be the boundary circulation of that whole lump? And the answer is, and I think I inadvertently highlighted over something important. The answer is, what I've got there is two separate little line integrals. This purple line integral going upward across that cut edge is oriented upward. The dark blue here go also on that same cut edge, but that's oriented downward. I actually have two little line integrals there, but they're over the same curve, but with opposite orientations. And remember, opposite orientations means that the values of those line integrals are negatives of each other. So what I have here is the same integral twice, but with opposite signs, and they cancel. So all of this disappears when you add them up. Let's take a quick moment on that before I proceed. Everybody okay with the argument that these two terms, the two different terms that I get on that shared edge, are going to cancel? Okay, well, sweet. With those gone, look at what remains. What remains is indeed the boundary line integral for the whole. So boundary circulation is an accumulating quantity because the whole is the sum of the parts. The whole is the sum of the parts exactly because of the cancellation across this shared edge. Does that make sense to everybody? Okay, this is our first example here of a sort of a phenomenon that we're going to see analogs of in various different circumstances over the next few weeks as we finish chapter 6 and 7. All right, so now real quick, I'm going to point out, and this is just for the geometric fun of it all, more than anything else. Let's look at some larger thing, and maybe I chop it into more pieces, right? If I have some great big thing here, and if I chop that up per all of these lines here, like that, and if for each one of these little regions, the rectangular ones, the non-rectangular ones, whatever, each little region, if I say, well, let's talk about the boundary circulation, well, on each one you're going to go counterclockwise, right? Region on your left. But so for this region right here, we go around that way, as indicated, and you do the same for every one of these regions. Look at all of the awesome cancellations. Like, so for example, the line integral on this edge right here. Well, that's going to show up twice. Once oriented that way as part of the boundary of that. Once oriented this way as part of the boundary of that. The line integral across this green edge is going to appear twice in the summation, but with opposite signs, and so it will cancel. And ditto every other interior edge. So it doesn't matter how many pieces you chop it up into, it remains let's see here. Let me do it like this. It remains, however many pieces you chop it up into, boundary circulation accumulates. Okay. All right, so now quick reminder. Why do we care about accumulation? Well, if a quantity accumulates, you can treat it like stuff, talk about its associated density, write down an integral theorem. We have ourselves an accumulating quantity. So we're going to treat it like stuff. I'm going to say it behaves like stuff, and compute the corresponding density and add it up with an integral. And here's the details of that. I am first going to talk about notation a little bit. Boundary circulation, when we talk about its density, I'm going to refer to the corresponding density as circulation density. I'm abbreviating here a little bit. I mean, the accumulating quantity in question is boundary circulation. Let me actually write this down just to be clear. This is boundary circulation. But you get tired of saying that after a certain amount of time. Anyway, circulation density, common term. And here's the formula for it. If you have a vector field P comma Q, the formula, and this is not obvious, by the way, there's a calculation that has to be done, and you can literally make a little region and literally let it get smaller and smaller, and different ways that you can approach the argument. The formula for boundary circulation is that right there. dq dx minus dp dy. It's wonderfully convenient. Nice and simple. This goes by many notations. Let's see here. I'm going to start by calling it curl. Y'all will recall that we talked about a version of curl back in Chapter 3. What we talked about back in Chapter 3 was a three-dimensional form of curl. This is a two-dimensional analog of that. We will eventually talk about the three-dimensional form of curl again, but because this, again, is highly analogous, this is also referred to as curl. That is a little bit of a source of confusion. We're using the same word for two, honestly, kind of different things. But nevertheless, common choice. It's called curl. Let me get to the rest of these notations in a minute. Let's finish spiking the football here. We have this quantity called circulation. We've made the observation that it is an accumulating quantity. Therefore, I can treat it like stuff. Therefore, I can talk about densities, and I can add it up with an integral. And the way you add it up with an integral, just like every other integral we've added up, is that stuff is density times size. Oh, I used the wrong color there. My density is curl. That's my density. That's the formula for it. And so you end up with this integral right here. Yeah, go ahead.
The only reason, though, is that it was accumulating because they canceled out, right?
Mm-hmm. Yep.
Is that the case for every single time? Or would
a
there be
case
where they don't cancel?
For boundary circulation, yes. That's
so they
right.
always cancel out.
Boundary
Okay.
Pronouns scare me to death. Boundary circulation specifically, yes. The cancellation on both sides, always.
Okay.
Yep.
Okay.
For the kind of stuff we're going to, I mean, look, there are some super weird, anomalous counterexamples that would nothing to do with Math219. But yeah, as far as we're concerned, always. Yeah. Okay, so this is the big theorem. This is what we call Green's theorem. That a line integral, specifically a boundary line integral, can be computed with a double integral of the curl operator. It's just, it's really surprising. If you think about it, wait a second, how could this possibly be? You're telling me that if I have a line integral, this is a intrinsically one-dimensional sort of calculation that we're going to do here, I can get the answer to that by not even thinking about the boundary, right? But by doing a double integral over the interior. It's like these two calculations happen in different places, but they always give you the same result. It's really surprising. So, let me go ahead and highlight then. This is called Green's theorem. All right, now back to the notations. Because it's called Green's theorem, I find it satisfying myself to refer to this integrand here as Green's operator, because it is the operator that makes Green's theorem work. And I don't know, I find that really natural. So I call it Green's operator. As a result of that, I also sometimes, in the past anyway, have written this as GRN, just as a little abbreviation of green, right? Because it's Green's operator. So I like that notation. If you look through my old exams, you'll see that that's in there, more than once, I'm pretty sure. But there are other notations, these other two notations. Let me, before I can talk about this one, wrote, let me talk about why, and reminder of what we're doing here. We're computing circulation, and let me pull your attention back to what we talked about last time of what is our interpretation of circulation. Like physically, how do we think of circulation? If F represents a flow of a fluid, circulation says I've got a closed curve and I'm measuring the extent to which the fluid is flowing along that curve that keeps kind of going around in the circle. In other words, it's measuring, in some sense, to what extent is the fluid kind of rotating around that curve. Well, curl says, yeah, that per unit area. So that says then, so Green's operator, aka curl, is saying how much of this overall rotation of fluid that's happening around the overall, how much of that is happening in the vicinity of a given point, and again per unit area because it's a density. And so because curl measures in some sense how much the fluid is rotating, rot is actually a pretty natural notation to use there. Okay, so I like that one as well. Go ahead and circle that. Yeah, go ahead.
So we're only looking at the rotation around the specific point, so not the entire curve?
So when you're talking about curl, you're talking about a density, you're talking about something that happens at a point. When you're talking about circulation happens over an entire curve. It's kind of a larger scale thing, right? And curl says whatever it is that's measuring, whatever that stuff is, how much of that stuff is there per unit area on the small scale. So it's a local measurement as opposed to a global measurement.
So when we multiply it by the area, then it becomes the entire thing.
Then it becomes a little piece.
A little piece of the
that you add up all of which to get the entire thing.
Okay.
Yeah. Right. All right. Okay. By the way, our textbook also likes to use this notation. I really don't like that notation. What weirds me out the most about this is they seem to be suggesting that they're going to do a cross product. Now, to be fair, this is a symbolic cross product. Yeah, right? But nevertheless, I mean, the way you're expected to actually crank this out is to pretend like this is a real cross product and write down the usual formulas. Well, cross products only work if your vector is three-dimensional. This isn't. So this gives me severe willies. I'm really uncomfortable with this, right? Now I know what Kali means when she writes this. And there is a point of view that makes this very natural, right? So I get it. I know where she's coming from. But I don't really see what advantage this notation offers that somehow isn't supplied by any of the several other alternatives that we have here. So you're never going to catch me using this notation other than when I'm talking about how I'm never going to use that notation. All right. Okay, so example. Hard problem, by the way. You got a curve given, you got a vector field given. You want to compute the line integral, it says. Vector line integral. let's take a quick moment to recognize how inconvenient this would be if we did it the old-fashioned way. The old-fashioned way being step 1, parameterize your curve. How do we parameterize a circle? Well, with sines and cosines. So x and y are sines and cosines. Okay, that means that's going to have to get plugged into your vector field. X and y, both being like sines and cosines, this is going to get weird, right? I think I am not optimistic about the resulting integral I'd have to write down if I were to brute force this calculation. Really strange integrand. I don't want to have to try to integrate that. Okay. All right. Now, alternatively, let's try to use our new theorem. Our new theorem says if you want to compute a line integral, cool. Do it with a double integral over the interior. Right? Everybody all right? Now there's an asterisk. This is a landmine. You do have to be really, really careful about this. Very often overlooked requirement in order to be able to apply this theorem. It says so right in the statement. Notice that your curve has to be a boundary. Very important, right? You cannot just compute any old random line integral with this theorem. This does not say any old random line integral. This says specifically vector line integral over, it says right there, boundary. Right? So many students make this mistake. It happens really often. So as I always do, I make a big deal out of things in the hope that the bigger a deal I make, the fewer students will step on this landmine. Don't forget, it's got to be a boundary. Okay, so now before we get too excited about this as a solution, let's look back at the question. Let's ask, is our curve a boundary? And our curve, you'll notice, clockwise oriented unit circle, which is like so. Is that a boundary? It's not. So we have a problem. Right? The theorem says boundary. This is not a boundary. Everybody see how we're got a little impasse here for the moment? So how do we get around this? The way we get around this is by turning this problem into a different problem. We're going to recognize that our curve, the clockwise oriented unit circle, that's our curve C. Well, that's closely related to the counterclockwise unit circle, which of course is a boundary. Right? If I were to go counterclockwise, like I have indicated in green here, all the way around, of course, that literally is the boundary of this solid disk on the inside. That's awesome. I could totally apply Green's theorem to this region here. Wouldn't that be nice? How can I relate that to what I'm interested in? Well, one is the same as the other, just oriented the other way, right? So you just have to make the realization that this is the opposite orientation, and therefore will give us the negative of the value of what we would get if we computed going the convenient direction. Yeah?
Why can't we compute it clockwise?
It's not that you can't, it's that you can't use this theorem. And we want to use this theorem because this theorem's awesome. And it says right here, boundary. Remember, boundary is an oriented thing, and it's oriented according to strict standard convention. Again, it was arbitrary, but that's how math has been set up, and that's the way we're doing business. And that means counterclockwise.
Oh, so it always has to be on the left.
The word boundary means counterclockwise. Now, you can orient something however you like. You just then can't call it a boundary if it doesn't follow the convention. Yeah. Okay, so, yeah. So now we are in business, right? We're just at the cost of inserting a minus sign and, giving some little brief explanation. Now, check it out. I am talking about an integral around a boundary. And if you want to compute a line integral around a boundary, sweet, we have Green's theorem. I can rewrite that as a double integral over the interior of the curl operator. That's Green's theorem on the previous page. That's the big gun. Right? Now, don't forget your minus signs, by the way. It's easy to accidentally forget. Don't forget to carry that along. And how am I going to compute that double integral of the curl? Let me clean up the mess here real quick. I've got to compute the formula for curl. Remember, the formula for curl is I've got to take dq dx. So I've got to take the x partial of that, which of course is just 3, and then minus dp dy. So I've got to take the y partial of that, which of course is just 1. 3 minus 1 is 2. Integral of 2 over the disk. Don't forget your minus sign. A little bit of arithmetic. And your answer is minus 2 pi. Everybody happy? Yeah.
So, like, interpreting what that final answer is.
Yeah.
Like if F were a fluid flow or something. Like
Yeah, okay, right. If F is a fluid flow, then we've computed this vector line integral, specifically a circulation. Circulation, this is going back to yesterday, or Wednesday's class. Circulation says, what is the total extent to which the fluid is flowing along the curve? And so loosely, intuitively, it's kind of measuring sort of an overall rotation of the fluid. Yeah. And since we got a negative answer, and keeping in mind that the curve is clockwise, effectively we were asking to what extent is this fluid kind of overall in some sense rotating clockwise, and the answer was negative something, and so that means it's actually overall kind of sort of rotating counterclockwise as it turns out. Yeah. Okay, another example. This is a little weirder. We have a curve here that's made up of various line segments. So like that, and then like this, and then like that, and then like this. Let's see here. So I guess I could parameterize all 4 of those line segments. You know, all else being equal, kind of prefer not to have to do that. It's 4 separate integrals. Not that we can't do it, but let's keep in mind that the purpose of an example isn't to get the answer. The purpose of the example is to illustrate a method, right? So let's use our new method, and let's think in terms of, hey, is this a boundary? Now, at the very first glance, you're going to be encouraged by the fact that when you're at that point and you're going in the direction indicated, that indeed, as it should be, the area is on your left. And that's nice. But notice here, as you're going in the direction that it says you're supposed to, now the region is no longer on your left. Now it's on your right. That's not what boundary means, and this curve is not a boundary. Yeah? So again, bummer. Again, there's a workaround. The clever workaround here is to just recognize that I can kind of chop this curve up into pieces in a different way. I'm going to view this curve as the sum of these 6 edges. Note the directions still totally work out, right? This is the same. I'm traveling all the same paths in all the same directions as was given, but I've just now sort of separated it in a different way. And notice those green pieces together are literally the boundary of the left triangle that I'm calling D1. And, well, what I have on the right is going exactly the wrong direction, right? It's, if you will, it's going clockwise around D2 instead of counterclockwise, which means that it's, whoops, wrong color. It's it's other than the orientation being wrong, which I can adapt by just putting that in there. That's the boundary of D2. So it's not a boundary, but I can really closely connect it to a couple of boundaries. And then the calculation is just based on that. And let's see here if I can get this to, there we go. So all together then, we've got the green integral plus the blue integral. The blue integral being oriented in exactly the wrong way, right, allows me to rewrite it then as the negative of a line integral around an actual boundary. And then these two integrals are easy to compute. That one already was a boundary, so Green's theorem, gotta love it. This one here now, I've fixed it into a boundary by dealing with the orientations, and so again, Green's theorem. Is that cool? Two separate little applications of Green's theorem there. Okay, yeah.
I still don't understand though, because it's still on the right.
Yeah, but you got to keep in mind that, so this integral here says boundary of D2. So that integral there in dark blue is going like so, which is a boundary. And I've accounted for the fact that the light blue that I'm responsible for and the dark blue that I prefer, I've accounted for the fact that they're opposites of each other with this minus sign. Yeah.
So because of the minus, you flipped it so to now that it's on the left.
So the dark blue curve that I have there is literally a boundary. It literally follows the rule that you just described. So yep, totally.
Okay, thank you.
Yep. So again, a little clever, clever little moves that allow you to turn hard problems into easy problems. Okay. And then yada 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 details. It turns out that a curl in this calculation is easy to compute. It's, again, dq dx, so I need the x partial of that, which is 5, and then I got to subtract dp dy, so I got to subtract the y partial of this, so I'm going to have altogether 5 minus -4, and altogether that gives me that curl is 9. And then, by the way, this has turned into a really easy problem at this point because all I have to do now, these are constant integrands, which means I'm really just interested in the areas, but the areas are the same, and so when you subtract, you get 0, and the whole thing disappears. And again, no fuss, no muss, right? No, I didn't have to parameterize anything. I didn't have to deal with any inconvenient integrands. And it all just falls into place. Awesome theorem. Okay, last thing I'm going to show you today. This is actually pretty quick. There's a really clever argument you can make if you write down Green's theorem as applied to a very particular vector field. I'm going to look at this vector field 0, x. Why? Because it's going to give me something I like in just a moment. Short answer. But notice what I have in green here is literally just Green's theorem as applied to this, or this special vector field that I've decided I want to look at. What's nice about it is that when you then compute this curl, you get 1. And what's nice about that is that makes this integral here just area. It's a slick move, right? Really clever. And the punchline then is that we have a vector line integral that will compute the area that you've enclosed with that curve. Really slick move. And now just a notational observation. Y'all will remember this coordinate line integral notation that I introduced last time, and I recently anyway. And most of the time, it's not that convenient. But look how nice it is when you write it. When you write this specific line integral with coordinate notation, it's actually very compact and convenient. So, in most cases, when you see this theorem, they're actually going to write it like this: the area is integral x dy, boundary integral x dy. Okay. Now, how do we compute this? Well, I would need to compute around the entire boundary of whatever my region is, and that's super inconvenient, you might say, but check this out. On any given single line segment, you could totally compute integral x dy on a single line segment. And this is a calculation I think everybody should do. Parameterize the line segment. You can totally parameterize a line segment. Plug and chug this integral computed only over one line segment, and what you will find is it simplifies super nicely. X bar delta y, the average value of x. So looking at this first segment here, for example, The average value of x is just 6.5. The change in y is just 5. Right? For this one line segment, super easy calculation. And then you just have to add that up over each of the line segments going all the way around so you trace out the entire boundary. And when you do that calculation, let's see here, multiplying for each and then adding up over the entire boundary, what you get is a nice, crisp, convenient answer that computes the area here for you. And notice how hard that area calculation would be otherwise. It'd be super hard, right? I mean, if you were to break this up into a bunch of triangles, none of them are right angles. It'd be monstrously inconvenient. And Green's theorem, this little special case of Green's theorem, kind of does it like with a magic wand. It just gives you the right answer. It's totally awesome. Okay, nice place to stop. See y'all later. Have a good rest of your Friday. Don't forget about attendance if you came in late.
Thank you.
Yeah, no worries. See you later.